Hello, everyone. Thank you. Thanks for coming. My name is Indradhanush, and today's talk is about how the habitat operator brings habitat awesomeness into Kubernetes. I am a software engineer at Kinvolk, and at Kinvolk, we are a Berlin-based engineering company with a few of us working remotely across the world, and we provide services on Kubernetes, container runtimes, Linux, and way down into the kernel. You can think of us as Linux geeks of the cloud-native space. We've been doing some work with the Habitat team at Chef to bring the power of Habitat into Kubernetes to extract the best of both worlds and see what we can do with it. In this talk, I'll be talking about what is Habitat and how it helps you to automate your deployments and how it does that. So before that, I'd like to just take a quick poll of how many of you have used Habitat before? OK, that's about 40% roughly, yeah. And how many of you have used Kubernetes before? Oh, more people. Awesome. I guess you're in the perfect place. After that, we'll be talking about what are Kubernetes operators and how and why they are needed in managing your applications. And we'll be looking at what we did with the Habitat operator as a result. But just having the operator in place is not really enough, because you need to be using something. Your applications need to be using the operator, because the job of the operator at the end of the day is to manage your applications, right? So without really having something that extracts the power of an operator, it doesn't make sense. So after giving you a walkthrough about the Habitat operator, I'll be giving you an idea about what the open service broker is, and also what is the service catalog. And including both of these concepts, we'll be talking about the Habitat service broker in the end. So moving on about what is Habitat. OK, I can go back. OK. So what's Habitat? If you've attended the keynote before, earlier today, you might have seen a nice demo by Nell. So what Habitat lets you do is automate your applications, automate the building and deploying your applications by supplying a plan file, which is the plan.sh file. And this plan.sh file creates a Habitat artifact, which is called the .heart file, which is nothing more than a tarball that Habitat understands how to extract and download and manage it around. A typical plan file might look like something this. Also, although this is a fairly minimal example. If you look at line number 1 and line number 2, that's the name of your Habitat package and the origin to which it belongs and the version. However, the most important line here is at line number 4, right? Which, if you take a quick close look, is core/curl. Now, core here itself is yet another Habitat origin, and curl is the name of yet another Habitat package. That means your Habitat dependencies are other Habitat artifacts themselves. In Habitat, in the earlier keynote, and also there was another talk at 2 p.m. today, there was a nice demo about the Habitat Studio. What the Habitat Studio does is gives you a clean slate locally every time you want to start from scratch without really messing up your dependencies on your local dev system. Now, it's all well and good to play around in the studio, but if you really want to be building your services, building your artifacts, you want something on the cloud. That brings you to the Habitat builder. The builder takes the plan.sh file and outputs a Habitat artifact and pushes it up to what's called the builder depot, which is normally located at bldr.habitat.sh. Now, to start a Habitat package, to run a Habitat application, you would be running the following command, the hab start origin/package name command. Now, when you do this, what Habitat does is it starts a Habitat supervisor. And the supervisor starts talking to the builder depot and fetches the latest artifact that's available there. Not only that, it will also keep a look for newer versions of your artifacts, and it will fetch, automatically download them, extract them, and update your service to the latest version. In this example, there's only one supervisor running, and the topology is called standalone. Now, it's pretty good to run a single instance, but more often than not, you would want to be running multiple instances of your applications for fault-tolerant systems. And if you run the same command with the topology as the leader flag that starts the first supervisor instance in the leader topology, the topology is a way of telling the supervisor that there's going to be more, or are you alone or not. Now, if you were to run another instance of your application with the same flag topology as leader, but an additional flag as peer, which is the IP address of your first supervisor. Now, they start talking amongst themselves. And you might not be happy with just 2, so you might want, let's have 3 for a minimally fault-reliant system. That's when you start the third supervisor, and this starts talking to the first because it knows the IP address of the first supervisor. Now, the supervisors use a gossip protocol to spread information amongst themselves, and that's when it can also be made aware of the second supervisor, thus forming what's called the supervisor ring. Most of the time, you will need to be configuring your applications. You will have a lot of time like a default set of configurations, and sometimes you would want custom configurations. By default, you can supply the default configuration in the default.toml file, and to customize it, you would place it in a user.toml file. Now, the slight difference here is that the default.toml file is included at build time, and user.toml can be included at runtime. So what the Habitat supervisor does is it looks for this user.toml file at the following path, which is hab user service name config user.toml, and keeps an eye out for that. And if you change the user.toml file, you can also get the supervisor to keep an eye out for changes and pick it up and restart your application with the upgraded configurations. Pretty cool, right? You can find out more about Habitat at the habitat.sh website or the project repo. The next part we'll be talking about is Kubernetes. Kubernetes is a cluster manager, scheduler, and orchestrator for your containerized applications. Now, what does that mean? Not only does it run your containerized applications, but at the same time, it also manages how and where and when to run them. For example, in your Kubernetes cluster, if you have one of your servers is running a lot of applications already, and it might not have the available resources, Kubernetes will decide on its own that, OK, this particular server is overloaded. Let's find space on something other. A very minimal Kubernetes cluster might look something like this, where you have 3 nodes, and one of them is the master node, and the others are the worker nodes. The master node is your point of contact for you, all of us, which we are the user. And to use Kubernetes and talk to the master node, we use this command line tool called kubectl, and we tell Kubernetes to apply the changes in a manifest.yaml file. The manifest.yaml file is your source of truth. Kubernetes will apply what you give it to it, and if anyone, whoever that is, makes any changes to those resources, and Kubernetes finds out that the changes in the state in your cluster does not match what you had supplied in the manifest.yaml file, it will very quickly revert it back to the manifest.yaml file. A more real-world cluster might look something like this, where you have multiple master nodes and multiple worker nodes for obviously having redundancy and having a fault-tolerant system. In worker nodes, you can run containers, one or more than one containers. And not all of these containers have to be the same. They can be different. They can be different from each other. They can be related. A lot of times, containers are also related. For example, in this example, you might want a database container and a web server to be running as one. They might have to share some common information around them. So Kubernetes introduces this concept for pods and brings multiple containers, multiple related containers in the same logical unit. Building on this concept of pods, you might also want multiple replicas of your pods at the same. So, OK, sorry, we'll come back to it in a bit. So in this example, if you take a close look at lines 1 and 2, At lines 1 and 2, we are telling Kubernetes what version of the object to be created and what is the object that's being created. So we are telling Kubernetes that create an object pod with version v1. We'll skip ahead to lines 5 to 12. And what we do here is we are telling Kubernetes that what is the specification of this pod, what are the contents of this pod. This pod, what it does is runs the busybox image, and it runs the sleep command once it downloads and starts the pod. Building onto the concept of pod is deployments. You build on multiple pods into one logical unit, and that's a deployment for you. Playing around with a deployment object, you can control the replicas that you want in your application. You can roll back your deployments, and as well, you can add auto-scaling on top of it. But a lot of times, most of the times, the containers will have ephemeral data. For example, so if the container gets deleted, your data is also lost. That's not a great feature to have when you're looking for building stateful applications. So to add to that, we have the concept of Kubernetes stateful sets. Now the name, as it tells you, it's stateful. It holds state. So it's similar to deployments, but it builds on top of it by adding persistent storage. A quick example can be Redis, where you, even if a pod gets deleted accidentally, you still want your data store to be safe and sound. Other things that the stateful sets adds is unique network identifiers. And what that means is if your pod gets deleted from one cluster, and at that point Kubernetes finds that, okay, this node does not have a lot of space, let's reschedule it to a different node, it will still find you the same network identifier. So your applications can still have the same network identifier, and they don't need to worry about changing network identifier. You can also order your deployments, and you can tell Kubernetes in what way to schedule your pods or and how to delete them. The next concept here is on Kubernetes is namespaces, which helps you segregate your parts of your cluster. A quick example of using namespaces could be having a namespace called production while having a namespace called staging. So now you can use the same cluster for deploying your production apps and your staging apps, but at the same time having complete isolation between them. Objects in different namespaces cannot interact with each other. The last concept about Kubernetes here we'll be talking about is Kubernetes Volume, which is an external storage that is mounted onto a pod using a volume mount. This tells Kubernetes that a particular data directory is available at a particular path inside the pod. That brings us to the end of this section on Kubernetes. You can find out more on Kubernetes on kubernetes.io or the GitHub project page. That's quite a lot of information, I agree. So I'd like to take a small pause here and ask if there are any questions at this point. Building onto a Kubernetes is a Kubernetes operator. If you think about an application like Postgres, it requires a lot of additional plumbing for things like database backups, auto vacuum, and things like that, right? At the same time, that's a lot of management headache that you don't want to be taking on your head. So what a Kubernetes operator does is takes this pain from you away and brings that logic inside the operator. So now this automates the management, the deployment of the applications into the operator. To extend this, we built the Habitat operator, and we did this so that we could manage Habitat artifacts, Habitat applications inside Kubernetes. In the start of a Habitat operator, what we have is the Habitat artifact, right? And Habitat has a feature where you can export Habitat artifacts into Docker images. So we use this feature to export Docker images and use this Docker image inside a Kubernetes pod. This is the rough overview of the Kubernetes operator. And to do that, we defined a custom resource, what is called the Habitat. And you can think of a custom resource as your custom type in like your own data type, but inside Kubernetes. Now this in the operator is again the source of truth. So if you make any changes, you must be making changes to the Habitat CRD. Any other changes will be, although they might be applied, the Habitat operator keeps a lookout that here's what I want, and here's someone has made this change, so it will go back and revert that change. So any changes must be made to the habitat CRD. A sample CRD definition looks like this. Now take a look at line 2 there. The kind is habitat, which tells Kubernetes that here's this custom resource that we want to be defining. And if you look around lines 8 to 12, that's telling habitat that this is the specific Docker image and how many replicas do you want. And under lines 10 to 12 are fields that map directly to the habitat concept itself, the name and the topology. In the habitat operator, we use the user terminal file as a Kubernetes secret. This is exactly what we were doing originally in habitat artifact itself for customizing our configurations. To do this, we created a Kubernetes secret, and we encoded the contents of the user.terminal file as a base64 string and put it under the key user.terminal right here. Now what this secret does is that now we have a Kubernetes object. We pass the name of the secret. Keep a lookout on the name here. We pass this name to the habitat CRD by the key config secret name. Now this tells Kubernetes that this specific habitat object needs to find this specific Kubernetes secret. And we use this Kubernetes secret inside a Kubernetes volume and mount it in the path where habitat expects it. So now if Kubernetes places the user.terminal file at that path, the habitat supervisor can pick up the changes in it and naturally apply them. In the first version of our habitat operator, called the V1 Beta 1, we were using Kubernetes deployments. But we moved to V1 Beta 2, and we used stateful set. The reason behind this was to support stateful applications like Redis. If you come back to this previous slide from a few minutes before, you can take a look. You can find that we're running multiple instances. Now, if you take a close look, not all the instances have the same number of arguments or even the same arguments. They don't have the exact same arguments. Now, this is a restriction in Kubernetes that if you need to run multiple replicas of your pods, you have to supply the exact same arguments. So we were thinking about how to get around this. And we came up with this solution of implementing a peer watch file in the habitat supervisor code itself. So we worked with the Chef team to add this feature in the habitat supervisor, where you pass a path to a particular file. Now what this file contains, it contains a list of IP addresses, and it's the IP address of all its peers. This IP address helps habitat supervisor to find its other peers and form the supervisor ring. This file is managed by the operator, and each time a new pod is created, it's updated. It updates this file, and each time a pod is deleted, it removes that specific entry from the file. And this file is mounted on to each pod at a specific path for habitat to find. So now we can run multiple pods and pass the path to the peer watch file. So now we have the same argument, but behind the scenes, each supervisor can find out its corresponding peers. OK, demo time.
I have a quick question.
Yes, please. Sure. So the question is that what is the specific use case that the habitat operator solves, right? Right. So if you were to run habitat applications inside Kubernetes, you will need to do a lot of manual stuff today. For example, you export the Docker image, and then you want to run it. But to bring the features of habitat itself, for example, the supervisor ring, which is especially useful for things like leader election. So let's say you're running a 3-node cluster of Redis, and you want a leader election to happen because you cannot have multiple write replicas at the same time. You only want one write replica, one write node, and the other have to be read replicas. So if you don't do this via the operator, then you cannot use the supervisor's code that does the leader election for you. So what we're doing here, we're taking the habitat artifact, running it in pods, but behind the scene, each pod has a supervisor wrapped inside. So the Docker image that we're using, it has the supervisor within it. So each pod is now running the habitat supervisor itself. Does that answer the question? No, not quite. So the follow-up question is that if this session is about that we must use habitat, did I get that right?
If you're running habitat and you want to run it in Kubernetes and you want to have the features like topology and things, the very first issue that we had was what Indra was talking about, having different command arguments. You cannot do that in Kubernetes, and so you're not going to have that feature at all. And so, yeah, it's basically impossible to do any kind of topology arrangements inside of Kubernetes if you have that. So the operator, the first thing it was doing was basically figuring out how to do this peer watch thing. And so it basically enables you to be able to run a feature-rich habitat. It gives you a feature-rich habitat environment inside of Kubernetes. And then I think Indra's going to talk about some additional things we're doing later, which is going to utilize some of Habitat's features. So.
Thanks, Rish. Okay, we'll move on with the demo. So, is this visible? Right at the back? Is it visible? Okay, cool. So I have the Habitat operator checked out on my system, and I already have a Minikube cluster up and running. So, and Minikube is a utility tool that lets you run Kubernetes cluster on your local machine. And what I'm going to do right now is I'm going to deploy the Habitat operator first. If you remember, we used the kubectl command for interacting with the Kubernetes cluster. The contents of this directory is resources that need to be created for the Habitat operator to function. And I'm happy to take a look inside this. So let's take a look at what's inside the rbac.yaml file. So what this does is it creates, so Rbac stands for role-based access control. And it's an authorization plugin in Kubernetes that helps you define roles and helps you isolate your resources and adds more security on your cluster. And what we're doing is we are creating specific roles that's required for the Habitat operator to create the resources. So we are giving Habitat operator the permissions to create a CRD, to permissions to play around along with deployment objects, with stateful objects. And in the minikube.yaml file, we have the cluster role that we need to create that is part of supporting Rbac itself. I'm going to now take a look at the status of the Habitat operator, which shows running here. So now that we have the Habitat operator up and running, we will deploy an example Habitat artifact. And before that, let me show you what I am going to be doing. In this example, I will be creating a Redis instance. So what this is going to do is it's going to start a Redis pod, and this uses the Docker image created from a Redis Habitat artifact. And I'm going to specify the count as 1 and the topology as standalone here. Now this is really important because at the next step of the deployment, I'll show you why. And I'm going to watch the pods. Okay. Oops. Too small. Okay. If you take a look at the first, is it still visible at the end?
Could be a bit bigger.
Okay. Thanks. So this is the pod that just got created. Now, normally what I'm going to do next is you wouldn't do that, which is execing inside this inside the container, but for the sake of the demonstration. So I'm getting into a bash shell, and I'm going to use the Redis client to connect to the Redis server that's already running. And I'm going to set a value to it, and then just verify that the value was set. Now, so let's get out, and while we take a quick look at the pods again, and we're going to delete this pod. So, and we expect that once we delete it, Kubernetes will start the pod again, and we expect the value x, which was 42, to be still present there. Keep an eye out on the status. Changes from terminating to creating, and now it will be very soon will be running. All right, we can exec back into the container. Again, this is not something normally you would do, but for this demonstration. Okay. So let's change this topology to leader and the count to 3. This is similar to what we had that image. If you recall, we had 3 supervisors. Now we apply this source of truth, which is we are modifying the habitat CRD route right here, right? So now we have this change, and we're going to apply. Oh, I need to get out. Yes. I'm going to apply this change again, and I'm going to also keep a quick look out. Okay. Okay, fast. Okay. It was just too fast before I could show you the watch command. So now you see that the first container, the habitat 0, is getting terminated because it needs to start up again with the latest configuration, which is the topology leader. Yes, you have a question? Someone? No? Okay, yes.
Just the persistent storage that you've just done.
Yes.
What is unique? So can I do the same thing without habitat? So what habitat makes here that it's so easy compared to just using, like, for example, mounting a distributed file system
Yes.
as a Kubernetes volume, and it is doable, not very easy, but doable. And storing the cache there. I'm trying to see what habitat makes it easier here. Like, if you can give us the sales pitch.
Okay.
That makes sense?
Yeah, okay. So the question is that what habitat makes it easier to do in regards to the persistence, right? Now, I feel it's a bit tangential, because this persistence is a feature that, like, if you forget about Kubernetes for a minute, and if you're running the Redis artifact for habitat, you would expect persistence out of the box, right? So now this persistence, which we added to Kubernetes, is just piggybacking and supporting that habitat feature inside of Kubernetes. Does that answer the question?
So habitat doesn't give me any advantage here.
Inside Kubernetes, no. This persistence thing is a requirement if you're running stateful apps, where you need your data to remain persistent, even if your pods get deleted and rescheduled onto a different, rescheduled again.
So let me rephrase that question. I'm coming back to my thing, and I'm saying, hey, we need to stop using what we're doing for Kubernetes management. Let's use habitat. How will the habitat operate, what you're showing us, will make our day-to-day life easier in your experience?
Yes. So the question is that how would using the habitat operator make things any different from what we are doing right now? So what the habitat operator adds is, if you are already running habitat as dedicated servers, now that's when you're not utilizing the full potential of your servers. You don't have the scheduling available to you. The moment you bring Kubernetes into the picture, you're bringing the power of habitat and adding Kubernetes into the picture. And what it does is, now it decides how to run your pods. If your servers are running out of resources, it takes care of that. It can add auto-scaling, and it can add more security policies for you in the form of Rbac. and pretty much every other Kubernetes pros under the tree. Okay.
Were you also asking why would you use Habitat?
So why would Habitat
10 minutes.
here to jump on getting already on Kubernetes? That was the question.
Yeah, so if we're looking, so I think you answered why would you use Kubernetes with Habitat?
Yep.
But if you're also asking the question, okay, I decided to use Kubernetes, now I want to use Habitat, then you look at the other things that Habitat gives you, like the control of your builds, and what they were demonstrating with the builder, and how you have that, you can, so what they showed on the keynote was when you make a change, it rebuilds, and then you promote it to stable, and then it auto deploys into your production cluster. What we would probably recommend is that you, when you have that, before you promote it to stable, that gets then deployed into a staging namespace in Kubernetes. Your CI stuff confirms that it's okay, and then it puts it into the production cluster. But so I think this building, this deploying, that's actually what you get added. The operator just allows you to use the Habitat applications.
Thanks, Chris. So we'll take our talk to the second half, and we'll go a bit faster because we're running out of time. So what is the open service broker, and why do we need it? So before I tell you about the open service broker, let me give you a scenario. What if you had a multi-provider setup, like you're using some services in a different cloud provider and something in a different cloud provider, and you wanted to use the feature set from one into another. Today, it might be very difficult for you because then there's a lot, you're not cloud agnostic and the other things. So what the open service broker does is it defines a common set of APIs that the cloud providers can implement. Now, and irrespective of who is providing the services, if there is a Postgres service that you want from, let's say, OpenShift inside your Cloud Foundry setup, you can still do it because both of them are talking the same API, which is the Open Service Broker API. Extending that concept is the service catalog, which is the Kubernetes implementation of the OSB API. Now, what the service catalog is, it's a registry of all the available applications in your cluster. So the service catalog, not only does it understand the OSB API, it also understands the Kubernetes concept. So if you can think of this fork in the middle that understands both the different languages and coordinates between the two. So in the cluster, the first requirement of running a service broker is having the service catalog up and running, which brings us to 3 new concepts. The service class, you can think of it as an available service. For example, a Postgres service, a Prometheus service, or a Redis service, and a service instance, as the name suggests, as an instance of the specific class. So which helps you that, okay, here, I want a new instance of Postgres, and then I want another instance of Postgres. So now you have one service class Postgres, but you can run multiple instances of the same service class. And the third concept here is service binding, and what it does is it adds additional configuration to your service instance. So when you bind to an instance, what you're effectively doing, you're adding an additional configuration that the service instance requires. We'll take a look of that in the demo as well. But before that, in the service broker, which is the question a few of you had, that why should you use the Habitat operator? So this brings you to the point why you should, what benefits you get while using the Habitat operator, because the service broker internally uses the Habitat operator to deploy and manage your application. So technically, you as an end user might not be the first point of contact for the operator. The service broker would be. So what the service broker right now can do, it can deploy Nginx, it can deploy Redis as a proof of concept, and it can deploy them in custom namespaces. So now you're talking to the service broker, which is deployed, and it can talk to multiple clouds. So now behind the scenes, it uses the Habitat operator to manage your Habitat artifacts and deploy them as and when they're needed. Another demo, and this is the last demo. So I will check out inside the service broker code, And how many of you have used Helm here? A few people. So Helm is a package manager for Kubernetes, and what it lets you do is define charts for your Kubernetes applications. We'll not dig into this because it's slightly out of context. So we use this to deploy our service broker, and it will create a new pod in a new namespace called habitat-broker, which all of which is already defined in that chart. I can give you the link towards the end of the talk, and you can take a look at that. Okay, so we are looking at this pod, and this last argument, which is slightly new this time, is telling Kubernetes, give me the pods running in the namespace habitat-broker. So you can see the status is running, but it's not quite yet ready. We want to be watching this. Oh, it's ready now. Awesome. So, and if I can bring you back to the slides, you notice there was something called svcat. Now, svcat is similar to kubectl, but this time it's a command line tool that helps you interact with the Open Service Broker API. And you can use this to get a list of brokers available in your cluster. The output looks slightly mangled. Better now. Okay, so we're going to be watching the status. Now, what this is doing behind the scenes, the service broker here is talking to the service catalog, if you remember, which understands the OSB API, and it's telling the OSB API, here are the list of services that I have, which is Nginx and Redis at the moment. Please register them. So if someone comes asking, please give it to them. Tell them that I can provide this service to you. And now you can see that the status is ready, which means the list has been registered on the service catalog. So now we want to take a look at what are the available service classes, which is what are the available. Sorry, I broke off in between. What are the available services in my cluster? Now, this can be from multiple brokers. So multiple brokers each having their own list of functionalities and combining into a list of services here. So now we have Nginx and Redis, and this demo we will be using Redis once again. Okay. All right. So I have a service instance manifest already defined. Now I should increase the font size. Yes. So if you take a look at here, we are telling Kubernetes to create a namespace for us. Where is the cursor? To create a namespace object called demo. So this helps us isolate all our changes inside the demo, inside this namespace. And we are telling the service catalog to create a service instance. Take a look at the kind here, which tells you that it's the service instance, and its name is going to be Redis, and the demo namespace that we want it to be created in. And to use this, like before, we can use the kubectl apply. Okay, and we want to watch. That was very fast. Okay, so now we have this Redis pod up and running, but if I exec into this container right now, it wouldn't make sense, right? We want to be using it from outside the cluster. So to be able to do that, we need to create a service binding, because we need to set a password at the very least against which we'll be authenticating with the Redis server. So to do that, I can show you the binding that I have here. And this creates a service binding. Now, behind the scenes, what the service binding does is it creates a Kubernetes secret. So let's get on with it. Okay, now the container is being terminated because the habitat operator detects that there's been a new configuration change that needs to be applied. So as a result, it's going to restart this container. And once the service binding has been created, what it does is it creates a Kubernetes secret object. This one right here. Okay, where is that? Yes. Oops. So this secret object is going to contain the configuration in the user.toml file. We want to take a look at what's inside this secret. Okay. So now if you take a look at this, the data that got created, so this is this is a base 64 encoded string. So we want to decode this out and take a look at what's inside this. Okay, so this specific line is the configuration that gets added to the Redis config. So now, if we use this password to authenticate against the Redis pod, we should be able to get in. But to be able to do that yet, we need to create a Kubernetes service which exposes your service outside the cluster and lets you connect to the service from outside the cluster itself. So very quickly, we'll apply the service manifest. Okay, where was that? And we'll take a look at the service that got created as a result. Oops. Right. So the node port here tells if you look at this type here, where is the cursor again? Okay, never mind. Under the type, you can look at the node port, right? And that tells Kubernetes that this particular port needs to be exposed outside the cluster. And look at the port mapping there. The 6379 port is the internal port, and it gets mapped to the port 30001 outside the cluster. Now, don't confuse it with the cluster IP here, because it's the IP address of the pod inside the cluster. But we are connecting to this pod from outside the cluster. As a result, we need to find out the IP address of the cluster itself. And we will be using this to connect into the cluster. I have the Redis CLI already available, and I'm going to use this. Okay, we're in. And let's just try setting something for now. The authentication is required. So, okay, I need the password. I forgot the password.
Indra, I'm just going to give you a heads up on the time.
Yeah, okay. Okay, Okay, we're going to have to do this again. The next thing I'm going to do after this talk is change my cursor's color. Can anyone find where the cursor is? Ah, okay. And also its size. Well, I thought it would be distracting for the audience. Please don't go away. I'm going to type this manually. Not this. Oh. Okay, and auth. Oh, that's a 0. Okay, so now what we've done is connected to the Redis pod from outside the cluster, which is what you would be doing in a typical scenario, is get the secret information out and use it in your application. And that brings us to the much awaited end of this talk.